When it comes to introduction, there is a part which known as background. So let's take a look on the background of this experiment. First of all, the shear force is crucial in structural design as excessive shear can cause sudden failure. This experiment measures the shear force in a beam under transverse loading and compares it with the theoretical expectations. The beam is cut at different distances and also demonstrating the effect of load position and magnitude on shear. And last but not least, comparing theoretical shear force with the experimental results help us to assess the validity and also the potential errors. Alright, let's take a look of the objectives of this experiment. First of all, to measure the shear force at a chosen section of a beam subjected to point loads. And the second is to calculate the theoretical shear force at the same section using principles of statics which known as free body equilibrium. And the third is to compare the measured shear force with the theoretical value and hence assess the accuracy of the apparatus and the validity of equilibrium analysis. Alright, let's take a look on importance of this experiment. First of all, to get a good understanding structural behavior, which is by systematically changing load positions and magnitudes, student can directly observe how shear distribution changes along a beam. This reinforces the concept of shear force diagrams used in structural engineering. And the second is relevance to engineering design. Since shear governs many real-world failures, example in beams and slabs. So from this, understanding and validating shear behavior can ensure safer and more efficient design. Figure of the experiment. So this figure known as ST012M shear force apparatus. There are 4 equipment that we used in this experiment, which known as weight hanger, applied weight, vertical spring balance and also horizontal spring balance. For a clear visual, I have attached the figure along with the names. Alright, so this is the procedure of this experiment. First, we show the beam was placed on the support and the distance between the supports was adjusted to 1 meter. With the load hangers, the spring reading and the shear force was recorded and taken as tear reading. And the weights were placed on the load hangers at the required position of the first set. The spring balance was adjusted until the beam was level again. The scale reading and the shear force taken. The steps were repeated at the same weight but with the position of set 2 and set 3. And finally, from the recorded data, the theoretical moment, measured moment and also the percentage difference between them were calculated.
We repeated this experiment 3 times. For each set, we kept the weight constant at 2 newtons. However, for the distance, we made it vary. For distance 1 of each set, we added an extra 50 millimeters for each set. For distance 2 and distance 3, we added 100 millimeters for each set. So the distance between the loads on the beam and the left support increases for each set. Before beginning our experiment, we had to take the tear reading of the scale reading and the shear. The tear reading is the reading of only the load hangers on the beam without any loads on it. After we have taken the tear readings, then we can move to the measured readings. The measured readings are the readings of the loads on the load hangers on the beam. After we have gotten the measured readings of both the scale reading and the shear, then we can calculate the experimental reading. The experimental reading is obtained by subtracting the measured reading to the tear reading. And for the shear force, the theoretical reading was calculated using a formula. If we were to compare the experimental shear force and the average theoretical shear force, as you can see, the experimental shear force is at a constant of only 1.2 newtons, even though the distance for each set increases. The average theoretical shear force increases as the distance increases, which proves the theory that the theoretical shear force will increase if the distance between the load and the support increases. The experimental shear force could be constant due to the equipment not being sensitive enough to detect the small variations in the shear force, or the load that we used of only 2 newtons was too light to detect the variations. The percentage error between the experimental shear force and the average theoretical shear force are quite low, with the lowest being in the second set of only 9.1%.
From the result, the table experimental shear versus average theoretical shear show that the experimental shear force stay constant at 1.2 Newton for all sets, while the theoretical shear force increased as the load moved farther from the support. This means the apparatus was not enough sensitive to measure small change. The percentage error decreased at the larger distance, showing the result is become more accurate.
So today I will explain the discussion part of this experiments. So first of all it is discrepancy between theoretical predictions and experimental results. The core of our discussion revolves around the clear and consistent discrepancy between our calculated theoretical values and the measured experimental data. It states that unequivocally that for a constant load, the shear force should increase linearly as the distance from the support increases. So our calculations confirms this and showing a clear progression from 0.9 Newton to 1.1 Newton and finally 1.3 Newton. The second one is apparatus limitations and systematic error. Firstly, the scale couldn't detect or display the small incremental change in force, such as difference between sets. It likely has a measurement threshold and causing it to report a consistent average value. And secondly, the their values like 13.8 Newton, 12.6 newtons and 12.2 Newton indicate the setup soft weight was significant compared to the small 2 Newton loads, potentially overshadowing the subtle variations in shear force. Third point of this discussion is analysis of decreasing percentage error. Our set 1 of 100 mm is the highest error, which is 33.3%. The theoretical shear force 0.9 Newton was smallest here. The apparatus' inability to measure such a small accurately resulted in the largest relative error. Therefore, set 3, which is 200 mm, was the lowest error, negative 7.7%, and the theoretical shear force was the largest here, which is 1.3. Fourth, theoretical validations. Despite the experimental issues, the theoretical calculations behave exactly as expected, which is the increasing theoretical values confidently confirm the fundamental engineering principle. For a constant load, the shear force at a support is directly proportional to the distance from that support. Lastly, the source of experimental error. Usually, parallax error in reading the analog scale, friction in the supports or pivots of the apparatus could resist motion.
In conclusion, the experiment showed the principle of shear force in simply supported beam. The results show that the shear force is between 0.2 to 1.8 Newton depending on the load position. The experimental shear force is remained constant and the calculated percentage error is 33.3, 91% and negative 7.7%. For the 3 set data indicate that the accuracy improved at the large load distance. Overall, we have proved the principle of static equilibrium and confirmed the reliability for the theoretical model in predicting beam behavior under different loading conditions.